Good morning, Tensor friends. Got a question here. What is the shift tensor for? In the playlist you're watching, my motivation was I wanted to understand Gaussian curvature. But since I've been studying a tensor calculus, I wanted to do it in a tensor format to find the relationship between Riemannian curvature and Gaussian the curvature. So that's what that entire playlist is for, is to get to the end, which is the famous theoremum egregium, the remarkable theorem from Gauss, which relates Gaussian curvature to Riemannian curvature. Okay, and I'd say 75% of all this work came from these two sources: Professor Pablo Grimfield's book, Introduction to Tensor Analysis of Calculus Moving Surfaces, and Professor Jim Fowler's YouTube channel, Tensor Calculus. Okay, that's where almost all of this came from. Now, full disclosure here, I'm not sure I'm qualified to answer this. I'm going to try, okay? It may not satisfy you. Warning. Okay, we have a position, the vector, that is in the three-dimensional Cartesian space here, right? And we want to convert that to, as an example, to spherical the coordinates, all right? So we would put in the transpose of x, y, and z. And we've done this many times, right? We've done this many times. So we take the partial derivative of this equation with respect to r, we get er. With respect to theta, we get e theta. With respect to phi, we get e phi. So we have three of these, the basis vectors now as a function of r, theta, and phi. All right. Now let's go look at this. Okay, so here is our Cartesian, the space, the 3D Cartesian space. Here's a position vector, which has a point on the end of it. All right, and that point now is a function of theta, phi. We've also done this many times, and the radius. Okay, now we want to leave the radius a constant. Excuse me. And we want to only study the surface of a sphere that intersects that point at a called a tangent plane. So there's a plane right at that point on this sphere. Okay, now on this tangent plane we can do calculus. So we can plot our basis vectors, e theta and e phi, and we can determine a metric tensor. We can do all this sexy stuff that you do in Riemannian the geometry. Okay, but before Riemannian geometry was Gaussian, and the Gaussian made reference to this space called ambient space. So this is a two-dimensional manifold. So the surface of a sphere is two-dimensional, and it's embedded in this what's called the ambient space. And Gauss made reference to that by including a normal. So this is e theta cross e phi gives that normal. Okay? That's what we needed to know. Okay, now back to where we were. So if we're interested in only studying the surface of that sphere, we have that position, we want to understand that position vector as a function of the surface, the coordinates, and they're written as s with a Greek index. But the surface, the coordinate itself is referenced to the ambient, the coordinates. So the ambient Cartesian, the coordinates are written as x of I. So we have a compound argument here, right? So if we want to find out how this changes with respect to that, we wind up with this on one side, and then the multivariable chain rule on this side. Okay, now we already know what the partial derivative of a position vector with respect to a coordinate is. Well, this is the same thing. It's just a surface coordinate or an ambient the coordinate. Okay, so this we call the covariant basis vector S alpha, and this we call the covariant basis vector EI. and they are related via this new thing, the partial derivative of a ambient coordinate with respect to a surface the coordinate. This is called the shift tensor, and it has two indexes. It has an ambient index and a surface index, right? So you can see the only free index here is alpha. So there's alpha here and alpha here, and this I is a summation index. Now on the surface of that sphere, we only have two coordinates, right? That we're interested in theta and phi. So we would expand this. There's the free index, a theta, 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 theta. Here's our summation index, would go x, y, z, and the exact same thing down here, except you changed the free index to the. So this is actually the equations of the surface, the basis of vectors. Okay. Now, since you're watching that playlist, you know how long it is, right? So I'm not going to reproduce that here because it's a lot. So you do about 4 more pages of tensor calculus, and you get to this relationship where the shift tensor is related to the Gaussian curvature by the covariant derivative, the covariant surface derivative of that shift tensor is related to the Gaussian curvature tensor by the components of that normal. Do you remember we just looked at that normal thing over there? So that's the relationship between the shift tensor and the Gaussian curvature tensors here. Now you continue on in that playlist and you do a lot more tensor calculus, like 4 more pages, and you finally get to the joke. Here's the end, is that the Riemann curvature tensor is related to the Gaussian temperature via this equation, and this is the theoremum egregium, the remarkable the theorem, okay, that relates what was referred to the curvature that you had to use the ambient space now no longer would need that. You can do all of the calculations you need on the surface of that manifold without any reference to it being in a higher dimension. Now you can understand why this was needed, because if you're in space-time, you have 4 dimensions there. What ambient space would you reference? I mean, is there a 5th dimension? We don't even know if there's a 4th dimension. There is in mathematics, but is there in reality? We don't know. So that's why this was needed, because we could no longer reference an ambient space when you got to higher dimensions. Okay? I think I answered that, but I'm not really sure. Let me know. All right, I'll see you later.